I think it's got to be the most exciting thing in science right now, is looking for life elsewhere. My name's Tami Rogers. I'm a professor of Computational Astrophysics here at Newcastle University. Physics is a subject that you can study and you could get lots of different kinds of jobs, right? You can do pretty much anything. So I did physics, and then I did a summer internship doing astrophysics, and I was like, that's for me. So planets are the planets we know of: Jupiter, Saturn, Venus, Uranus, etc., etc. They're the ones that go around our sun. Exoplanets go around other stars. We know quite a lot about them. We've discovered all kinds of different exoplanets. They're very different than the ones that are in our current solar system. Some are like the ones in our current solar system. Some are very, very different. The first exoplanet was discovered around 1992, and there's about 4,000 have been detected now since then. 2 or 3 years ago, there was a system called the Trappist system that was discovered that has 7 exoplanets orbiting a star a little bit less massive than the sun, and about 3 of them we think are habitable. So in a habitable zone, have a temperature where you could have water on the surface. So it is a fairly new field, if you call 1992 new. It's still growing, I think. We're still looking for the other Earth. And there have been some planets out there that people call Earth 2.0 that are like Earth in some ways. There's 2 main detection methods that have been used to find them. The first method was called the radial velocity method. So when Earth goes around the sun, the Earth doesn't actually go around the sun exactly. The Earth and the sun go around a center of mass, and they both orbit around that center of mass. It turns out in the Earth-Sun case, the center of mass is very close to the center of the sun because the sun is so much bigger than the Earth. But in these planets around other stars, that could be different. So what happens is the planet and the star go around a center of mass. That makes the star wobble. And that wobble of the star causes the starlight to be Doppler shifted. And we call that the radial velocity method, when we see the starlight of the star Doppler shifted to and away from us. And that little tiny Doppler shift we can measure, and then because of that we can infer the existence of a planet and get its mass actually from Kepler's laws, so from very basic physics. The second method is called the transit method. And this has become revolutionized with the space telescope called Kepler, which is a NASA telescope. And what it does is it looks at the same space of sky, just stares for years. And it looks for dips in starlight. Let's imagine you're looking at a star, and the star has a constant brightness, and then all of a sudden the brightness dips just a very, very little bit. And that happens because the planet happens to pass in front of the star. And when that happens, we call it a transit because the planet transited in front of the star. And then we can also infer the existence of a planet. Now you can imagine that's very lucky because all stars and planets aren't oriented in a way such that we see the dip in the light. So the ones we see, we happen to be lucky enough to see in that configuration. A few years ago, there was a study about how many planets we think are in the galaxy. And it turns out we think there's at least 1 planet for every star. And there's 100 billion or more stars in our galaxy. So there's hundreds of billions of planets out there just within our galaxy. NASA announced a mission called Dragonfly that's going to go forward. And Dragonfly is going to go to the moon of Saturn called Titan. That's the name of one of my dogs, by the way. It's going to go to Titan, and it's going to look for signs of life, actually. Titan is this moon of Saturn. It has a nitrogen atmosphere like Earth's, is one of those things you look for. It's got methane lakes. It's got a lot of things that might be conducive to life. So there's a lot of things going on looking for life in exoplanets, maybe through their spectra, but also life on other bodies here in the solar system. So I do numerical simulations, so that means I put big equations on a big computer, and by big computer I mean thousands of processors at once. When you look at other planets, you don't see the planet. You can't, because the starlight is too bright, right? It washes it out. So you have to look for very interesting things like how the light changes as the planet goes around the star, right? So the observers that are doing these observations, it's amazing what they can do, right? But somebody made a prediction about what the atmosphere of this planet would be like, and then the observers went out and they confirmed it. And then Later on, I did some simulations that said actually the atmosphere will do something else in this one particular regime, and the observers went out and they saw it. And so that's very exciting, right? When you can predict something that's observable, that's fun. The exoplanet field, that's going in the way of what kind of planets can be habitable, what kind of planets are out there and can even exist, because the planets that make up our solar system aren't everything. We've learned that. And so what kind of planetary architectures can exist, and what are they made up of? Can they support life? Those kind of things. That's the field of exoplanets and where it's going.